Hello everyone, welcome to the next session on algorithmic problem solving. In this session, we would like to look at the problem of zeroing out the rows and columns of a two-dimensional Boolean matrix. So essentially, the idea is to zero out a row which has any zero and zero out a column which has any zero. So how do we do that for the entire matrix? So let us look at the solution.
The input to our problem is a two-dimensional matrix A with m rows and n columns. We need to zero out any row of matrix A which has one or more zeros to start with. Likewise, we need to zero out any column of matrix A which has one or more zeros to start with. In the example shown, input matrix A has a 0 in the upper row and left column. Accordingly, the entire upper row and left column are zeroed out in the output. In our examples, for simplicity of exposition, we will assume m is equal to n. Generalizing to the case of unequal m and n is simple. Here is the pseudocode and the Python code snippet for a simple brute force algorithm for the problem. We create a copy B of the input matrix A. We loop through all rows and columns of the matrix A. If any entry is 0, we simply zero out the corresponding row and column of B. For a matrix with n rows and n columns, the algorithm has a time complexity of order n cube. The algorithm also uses an additional order n square space for storing the copy of the input matrix. Now let us look at the pseudocode and Python code snippet to implement an improved algorithm. We define an auxiliary array zeroOut row to indicate which rows need to be zeroed out. Similarly, we define an auxiliary array zeroOut call to indicate which columns need to be zeroed out. Both these arrays are initialized to all zeros. We loop through all entries of the matrix A. If the entry in matrix A in the ith row and jth column is 0, we set the value of zeroOut row, I, to be 1. We also set the value of zeroOut call, j, to 1. This part of the computation takes order n square time. Next, we walk through the array zeroOut row. If the ith entry is 1, we zero out the ith row. Then, we walk through the array zeroOut call. If the jth entry is 1, we zero out the jth column. These computations take another order n square time. Is there any advantage of identifying all rows and columns to be zeroed out a priori? The answer is yes, since in the previous version of the algorithm, if there are k zeros in a row or column, the row or column was being zeroed out k times. By avoiding these redundant computations, we have managed to reduce the overall time complexity from order n cube to order n square. The space complexity is order n square, including the order n square space used by the copy B of matrix A, and order n space used by the arrays zeroOut row and zeroOut call. Let us develop the ideas for an in-place algorithm. Consider the example shown. First, we note that row 0 needs to be zeroed out, but column 0 does not. We will use row 0 to record which columns with index greater than 0 need to be zeroed out. We will use column 0 to record which rows with index greater than 0 need to be zeroed out. Note carefully that we do not lose any information by this overwriting, since elements overwritten are ones which will be zeroed out in future anyway. Also, we have already noted upfront whether or not row 0 or column 0 have 0 entries themselves. We locate zeros outside row 0 and column 0. Then, we mark the corresponding positions in row 0 and column 0 as shown in the example. We note the rows to be zeroed out. We zero out rows with indices greater than 0, which we have marked for the same. We note the columns to be zeroed out. We zero out columns with indices greater than 0, which we have marked for the same. Now, recall that we had noted up front that row 0 needed to be zeroed out as well. Finally, we zero out row 0. Note that we accomplished the task without using a copy of the matrix. Also, we have done away with the row and column vectors storing information about which rows and columns are to be zeroed out. These pieces of information were stored in row 0 and column 0 respectively. We summarize the ideas presented in the previous example in the form of the algorithm pseudocode and Python code snippet. The input is a two-dimensional array A. Here we have assumed an array with n rows and n columns. but the solution can be extended to any number of rows and columns. We initialize the flags zeroOut row 0 and zeroOut col 0 to false. If there are any zeros in row 0, we set zeroOut row 0 to true. Likewise, if there are any zeros in column 0, we set zeroOut col 0 to true. We now try to record the information about which rows numbered greater than 0 and columns numbered greater than 0 need to be zeroed out. We mark in row 0, which columns need to be zeroed out. We mark in column 0, which rows need to be zeroed out. Recall that we already have noted up front whether or not row 0 and column 0 need to be zeroed out. We loop through column 0, starting at index position 1. If any entry is 0, the entire row is zeroed out. Next, we loop through row 0, starting at index position 1. If any entry is 0, the entire column is zeroed out. Finally, we check back the Boolean flags zeroOut row 0 and zeroOut col 0. We zero out row 0 and column 0 if the corresponding flags are set. Time for a quick question. What is the time complexity of the in-place algorithm presented for a matrix with n rows and n columns? Option A, order n. Option B, order n log n. Option C, order n square. Option D, order n cube. The correct answer is option C, order n square. Comparisons of the algorithm are shown in the table. From zeroOut 1 to zeroOut 2, we managed to improve the time complexity by an order of magnitude to order n square. From zeroOut 2 to zeroOut 3, we shaved the requirements of the extra space from order n square to order 1. Thank you. This course is brought to you by Elahay Technologies.